Welcome to our comprehensive guide on relational database concepts. Understanding these fundamentals is crucial for anyone working with data in machine learning and data science applications. Relational databases are structured systems that organize data into tables with defined relationships. They provide a reliable foundation for storing, retrieving, and managing the vast amounts of data that power modern machine learning applications. Here's an example of a relational database schema for a movie rental system. Notice how different entities like members, rentals, and movies are organized into separate tables with clear relationships between them. For machine learning practitioners, relational databases are essential because they provide clean, structured data that can be easily queried and transformed for model training. They ensure data quality and consistency, which are critical for successful machine learning projects. Throughout this series, we'll explore 8 fundamental concepts that form the backbone of relational database systems. Each concept builds upon the previous ones to create a comprehensive understanding. Here's another example showing a more complex database schema with multiple interconnected tables. This demonstrates how real-world applications organize data across different entities like users, devices, purchases, and analytics. By mastering these relational database concepts, you'll have the foundation needed to effectively work with data in machine learning projects. You'll understand how to structure data, write efficient queries, and maintain data integrity throughout your ML pipeline. Database keys are fundamental concepts that ensure data integrity and establish relationships between tables. Understanding the different types of keys is essential for effective database design. Let's start with the superkey, which is the foundation for understanding all other key types. A superkey is any collection of attributes whose values uniquely determine a tuple in a relation. For example, in a student table, the student ID alone could be a superkey, but so could the combination of student ID and name, or even all attributes together. The key requirement is uniqueness. Now let's examine candidate keys. A candidate key is a minimal superkey, meaning if you remove any attribute from it, the collection would no longer uniquely identify tuples. Here's a practical example using one of our database images. This student table shows different types of keys clearly marked. From the candidate keys available, database designers choose one as the primary key. The primary key is the designated candidate key used to uniquely identify tuples within a table. Primary keys have special properties. They cannot be null, must be unique, and should remain stable over time. They serve as the foundation for establishing relationships between tables. Finally, we have foreign keys, which create the vital links between tables. A foreign key is a set of attributes in one table that refers to the primary key of another table. This diagram shows a perfect example of foreign key relationships. Notice how the course ID in the student table references the course ID primary key in the course table, creating a meaningful connection. Let's examine a more complex example with multiple tables and relationships. This airline database schema demonstrates how different types of keys work together in a real-world scenario. Here we can see how primary keys in one table become foreign keys in related tables, creating a network of relationships that maintain data integrity and enable complex queries across multiple tables. Understanding these key concepts is essential for database design. Superkeys provide the foundation, candidate keys offer minimal uniqueness, primary keys serve as the chosen identifier, and foreign keys establish crucial relationships between tables. SFW queries are the foundation of SQL, representing the 3 essential components that allow us to extract specific data from databases: select, from, and where. SQL, which stands for Structured Query Language, provides us with powerful tools to interact with relational databases. The SFW pattern forms the backbone of most database queries. Every SFW query consists of 3 main components. Select specifies which columns we want to retrieve. From tells us which table to get the data from. Where allows us to filter the results based on specific conditions. Here we have a customer database table with columns for customer ID, first name, last name, age, and country. This table contains all the customer information we might want to query. The query shown selects only the first name and last name columns from the customer's table. Notice how select specifies exactly which columns we want, and from tells us the source table. Now let's look at a more complex example using an employee table. This table contains employee information, including their work location and assigned projects. This query demonstrates all three SFW components. Select chooses specific columns, from specifies the employees table, and where filters for only employees working in New York. Here we see a complete example showing both the query and its results. The query selects product ID, name, and sell start date from the product table, filtering for products where the year is 2005. The results show exactly the data that matches our criteria. Remember these key points about SFW queries. Select determines which columns appear in your results. From specifies the source table. Where filters rows based on conditions. And all three components work together to extract exactly the data you need from your database. Database operations are essential tools for working with relational data. The two most fundamental operations are join and union, which allow us to combine data in different ways. Let's start with join operations. A join combines rows from two or more tables based on a related column between them. This is fundamental to relational databases. Here's a practical example. We have a customers table with customer information and an orders table with order details. Both tables share a customer ID field. When we join these tables on the customer ID, we get a combined result that shows customer information alongside their orders. This is an inner join, the most common type. There are several types of join operations. Let's explore them using Venn diagrams to visualize how they work. Inner join returns only rows that have matching values in both tables. Left join returns all rows from the left table and matched rows from the right. Right join does the opposite, and full outer join returns all rows from both tables. Now let's look at union operations. Union combines the result sets of two or more select statements into a single result set, eliminating duplicate rows. Here's a practical example of union. We have separate tables for teachers and students, and we want to combine all ages into a single list. Let's see the SQL syntax for these operations. Join uses the join keyword with on to specify the relationship, while union simply combines select statements. These database operations are essential for data analysis and reporting. Join operations help you combine related data from multiple tables, while union operations help consolidate similar data from different sources. In relational databases, tables don't exist in isolation. They are connected through relationships that help organize data efficiently and maintain data integrity. There are three main types of relationships between tables: one-to-one, one-to-many, and many-to-many. Each type serves different purposes in database design. A one-to-many relationship is the most common type. Here we see an order table connected to an order detail table. One order can have multiple order details, but each order detail belongs to exactly one order. The order ID serves as a foreign key in the order detail table. Many-to-many relationships require a special approach. Here we see books and authors connected through a junction table called book author. This allows one book to have multiple authors and one author to write multiple books. The junction table contains foreign keys from both related tables. Normalization is a fundamental database design principle. It involves organizing data across multiple tables to eliminate redundancy and maintain data integrity. This process brings several important benefits to database systems. In real-world applications, databases become much more complex, involving multiple tables with various types of relationships. This genomics database example shows how many tables can be interconnected through primary and foreign key relationships, creating a comprehensive data model that maintains integrity while supporting complex queries. Understanding table relationships and normalization is essential for effective database design. These concepts ensure data integrity, reduce redundancy, and enable efficient querying across multiple related tables in complex database systems. Modern database technology is rapidly evolving with artificial intelligence and machine learning integration. Today's databases are becoming smarter, more automated, and better suited for complex data processing tasks. AI-driven databases represent a major advancement in database technology. These systems automatically handle complex tasks that previously required manual database administration, including indexing optimization, query performance tuning, and resource management. Advanced systems like NEO use machine learning to optimize database query execution. These systems learn from past query patterns and automatically select the most efficient execution plans, significantly improving database performance. Vector databases are specifically designed to handle the complex numerical data generated by machine learning models. These databases excel at storing embeddings and performing similarity searches across high-dimensional data. This diagram shows how different data types are transformed into vector embeddings. Images, text, audio, and video are processed through specialized neural networks to create numerical representations that vector databases can efficiently store and query. Schema simplification addresses the challenge of complex database structures. Traditional multi-table schemas with numerous relationships can be difficult for AI models to navigate when generating SQL queries. Schema simplification techniques flatten these complex structures into single-table formats. This transformation makes it much easier for machine learning models to understand the data structure and generate accurate SQL queries. These modern database technologies deliver significant performance improvements. AI-driven optimization can reduce query execution time by 40 to 60%, while automation reduces the need for manual database administration. These trends represent the future of database technology, where artificial intelligence handles complex optimization tasks automatically, making databases more efficient and accessible for machine learning applications. Database concepts we've explored are not just theoretical. They power critical systems across every industry. From managing your bank account to recommending your next purchase, these principles drive the digital world around us. Let's examine a complex database schema from a real business system. This entity relationship diagram shows how multiple tables work together to manage books, DVDs, customers, and transactions in a retail environment. Customer relationship management systems rely heavily on well-structured databases. This diagram shows how customer data, campaigns, opportunities, and contacts are interconnected, enabling businesses to track every interaction and optimize their sales processes. E-commerce platforms demonstrate the power of multi-tier database architectures. This two-tier system shows how user interfaces connect to database management systems, enabling millions of customers to browse products, make purchases, and track orders simultaneously. Machine learning applications represent the cutting edge of database utilization. This pipeline shows how databases feed clean, structured data into machine learning models. Recommendation systems, for example, use relational databases to store user preferences, product catalogs, and interaction histories. Industry experts consistently emphasize that understanding these database fundamentals is crucial for success in data science and machine learning. Proper schema design, efficient querying, and data integrity practices directly impact model performance and business outcomes. These database concepts form the foundation of modern data management. Whether you're building financial systems, e-commerce platforms, or machine learning applications, mastering these principles will enable you to create robust, scalable, and efficient data solutions.